Okay, thank you very much. I'm always sad when it's the last class, because I'm used now to all of you, to your faces, to your questions. All of you are interesting. I prepared some projections for today, but before that, I thought I have to do a small compliment. In fact, two things. One thing is about transverse measured foliations. So we know what is a measured foliation. This is a foliation, and I can measure the kind of length. There's a measure on each transverse line, and it's invariant. So this transverse segment here and this transverse segment, there's a natural map between them. I send every point to the point which is on the same leaf, right? And this natural map is measure preserving. This is a measured this is transverse measure for the foliation. There are more general transverse structures. For instance, a foliation is said, instead of being transversely measured, it can be transversely projective, and meaning that these maps are projective. These local maps are projective, or they are much more complicated transverse structure. Anyway, so this is a transverse. And then we talked about, I showed you a picture, and we talked about now transverse measured foliations. And we said that transverse measured foliations are like this. Transversality is just a mathematical notion, which means that they intersect. With a definite angle, if you want. So this intersection is not transverse because here it's tangent. Okay, so transverse means just transverse means that you can think of intersecting with a positive angle. So transverse measured foliations. So we have two measured foliations. So locally it's like this, but then I have to decide. I have to say okay, thank you. You did it. I have to say what happens at the singular points, and since there are some finite number of configurations at the singular point, it suffices to say how they are at these singular points, or at these, and so on. Okay, so I have transverse measured foliations. We talked about quasi-conformal maps. These are the maps which send the local infinitesimal circles to infinitesimal ellipses, and this ratio here, is bounded. This is the meaning of quasi-conformal. So, and what I want to make the relation. In fact, we said that there is a Teichmüller distance on Teichmüller space. This is much before Thurston defined his distance, maybe 40 years before. And the thing which I want to say is that transverse measured foliations describe geodesics for this metric. So when I started this course, I said, okay, we are going to define a metric and on some space, and what are the good questions after we define a metric? One of the good questions is, can you describe the geodesics for this metric, right? We did this for the hyperbolic plane, we did this for the Euclidean plane. On the sphere, we said geodesics are. So now I have a metric on Teichmüller space. I have two metrics. We define two metrics, the Thurston metric and the Teichmüller metric, which I defined. And okay, so what is the relation with transverse measured foliations? So first, let me note that a surface equipped with what? With two transverse measured foliations carries naturally a metric. So you see, the surface is like this, a surface, and it is filled with this measured foliation, and it is filled also with the other measured foliation, which is transverse. Now, I say that this surface is equipped with a metric. Is there a natural metric you see here on this surface? Yes, no, not necessarily the taxicab metric. No, because I mean, no, it's not the taxicab metric. It's something more easier than the taxicab metric, because you know to go from here to here, I don't need to do this. I just follow this. I just follow this straight line, like in the Euclidean plane.
But what is the straight line?
Yeah, this is what are these? What is this metric? A pair of transverse measured foliations define a metric on the surface. And I'm asking, what is this metric? Well, I take a point here. I have this natural squares. I can send them to squares in the Euclidean plane. By isometries, in fact, because this is Euclidean and this is Euclidean. I mean the distances when we said we have a transverse measure. The transverse measure is Euclidean, right? There's no other way here than sending this to this portion to a portion of the Euclidean plane by sending horizontals to horizontals and verticals to verticals. Here I have a notion of horizontal and vertical, and then I have a notion of length here. I have a notion of length which comes from the transverse measure. Okay, so in fact I have charts. I have charts for this surface equipped with these transverse measured foliations, and the coordinate charts are Euclidean isometries because of this invariance of the. If I take another chart like this, you see this is the same length, and so on. Okay, so let me write this here. Carries a metric which is Euclidean, except what? Except, yes, at the singularities, because I told you what happens here, but I didn't tell you, here at the, a neighborhood of the singular point, I cannot send it isometrically to the Euclidean plane, right? Because here I have, it is like I'm gluing, I am gluing 1, 2, 3, 4, 5, 6 rectangles along a single vertex, and I destroyed the Euclidean metric. So a Euclidean metric on the complement of the singularities, on the complement and at the singularities, I have a special structure which, you could think about this at the singularities. So this is called, in fact, this is called a singular flat means Euclidean. Singular means I have singularities. A singular flat metric with cone-like singularities, and I can compute there's a cone angle. I can compute the cone angle at each singular point. Let me take a very simple example. So this is a surface, the surface of this parallelepiped. Here I have foliations perpendiculars to the boundaries of my rectangle. Here I have two foliations, so on. I'm taking a Euclidean parallelepiped, and I declare that these foliations, these two transverse foliations, are measured foliations. Since I want to say that the transverse measure of the arc of this arc, you see, is exactly the Euclidean, its Euclidean measure when I project it on one of the sides, and I do this for when I do this for all these arcs. I can continue on the surface. So this is an example of I call this a singular flat structure, singular flat metric. This is an interesting example of a singular flat metric. It is not Euclidean. It is Euclidean with singularities. Each point here, or even on the edges has a Euclidean neighborhood, except at the angles. At the angles, there's no Euclidean chart which sends this to the Euclidean plane, because here I have a singular point where the total angle, how much is the total angle around my, so an insect sitting here, he looks at all the directions, at all his horizons, and he measures the total angle around him. So how much is the total angle? 17? What did you say? 3 pi over 2. 3 pi over 2. This is why. So somebody can live on this parallelepiped, but when he arrives at this point, the total angle at the horizon. So this is why it's a singular metric. 3 pi over 2. Somebody told me 3 pi over 4. Did you say 3 pi? Okay. No, because I don't. I mean, I don't mind because I'm like this. Okay, 3 pi over 2. Okay. So let me say several things now again. No, let me first finish with it. So there's this Teichmüller metric we talked about, and I said I want to tell you how are the geodesics of the Teichmüller metrics. So a geodesic means I mean it means many things, but in particular I have to tell you a path in this space of metrics, right? And then I will tell you that this path is geodesic. So I come back to my general surface equipped with two transverse measured foliations. What can I do with what is the simplest thing I can do when I have two transverse measured foliations, or one measured foliation? If I have a measured foliation on the surface, I can say, okay, I obtain another measured foliation by multiplying the measure by some constant, right? Okay, so in principle, this is kind of box in my measured foliation. If I multiply the transverse measure by 2, then I want to imagine the new metric, in fact, as 2 times larger, so like this. So in terms of the local charts, I'm saying the new local chart for my metric will be extended by 2. Will be multiplied by 2. Okay, so here I have two measured foliation, which are transverse, and I want to treat them equally in the same way. So I will shorten the one and narrow. I will make the second one more narrow. So there is a natural map here from my initial surface, this surface here, to a new surface where I multiplied one of the transverse measures by 2, and I divided the other one by 2. Okay, I did this, in fact, because I want to keep the area of the surface the same. So the first thing you understand is that I obtain another surface. I'm obtaining another surface from the geometric point of view, even if the surface will not change topologically. I am obtaining another surface. The second thing I want you to notice, you have to imagine, is that okay, I told you this change of coordinates, which change the Euclidean structure at a point which is not a singular point, but you must imagine that, okay, all these things I'm doing are compatible at singular points. At the singular points, I'm doing the same thing on all these sides. So I get the required result. That is, I get a singular flat structure with the required singularities. Okay. So this defines a path, that is a continuous curve, a path in what? Where is this curve? Yes, in my space of metrics, that is in my Teichmüller space. Okay, this defines a path in Teichmüller space. And what I'm saying is that this path, this path is a geodesic for the Teichmüller metric. This is a very important result, in fact. So this Teichmüller metric, I described you some geodesic paths, and there's a Teichmüller existence and also a uniqueness theorem. Let me just state it here. So this is also proved. This was proved by Teichmüller existence and uniqueness theorem. Any 2 points in Teichmüller space can be joined by a unique geodesic. I mean, it is understood here that for any two, so you remember the Teichmüller space is a distance between two surfaces, and these two surfaces in this setting are complex surfaces. They are not metric surfaces, they are complex surfaces. We are measuring distances, quasi-conformal distances. We are measuring what is the best map which deforms, which is close to a conformal map, which is not, in general, it is not conformal. The surfaces I'm talking about are Riemann surfaces. They are not metric surfaces. The theorem there says, well, I take two surfaces, like two Riemann surfaces. I can construct a pair of transverse measured foliations on the first surface such that the complex structure induced by this metric is the one of this surface. Okay, these are complex surfaces, and a metric induces. I mean, when you have a metric, then you have an underlying notion of angle, and the notion of putting a complex structure on a surface is just a way of measuring angles. Okay, so the theorem says that I can find a pair of measured foliations and a path in the space of measured foliation. This path is, this path is, I said here I multiply by 2 and I divide by 2, but then I can multiply by t and divide by t. This path is a geodesic. This path is a shortest path in Teichmüller space.
Is this independent of the foliation that we choose?
No. For each two surfaces, I give you two surfaces, and the theorem is an existence theorem. It says there exist foliation on this surface and a transverse foliation. The two foliations depend on this surface and on this one, because they give you the direction on which you have to stretch and contract to arrive to the other surface. Yes. Maybe there's a last thing which I did not explain to you, and which now I think is important to emphasize. What is a geodesic? Mm-hmm. So here I have, you see, I have only a geodesic. You know what is a geodesic in Euclidean plane, in hyperbolic plane, in the sphere. And now I'm talking about geodesics in complicated spaces, in fact, which, I mean, this Teichmüller space and the Teichmüller. Yes, tell me. Well, yes, it has to exist. It has to exist. So in the existence theorem, it says that geodesics exist in the theorem. It yes. Sometimes geodesics do not exist. Yes, yes. Shortest paths do not exist in some. I mean, in general they exist, but let's say in some. Okay, so what is a geodesic? What is a geodesic? What is a geodesic here? Somebody can have an idea? I want a geodesic, so I just have M with a distance, let's call it X, a metric space, and I have 2 points in a metric space, and I have a path from one point X to a point Y. So we will suppose that the space is path connected. In order I will define a geodesic in terms of a path. So I have a path. I want to say that this path is geodesic. So I suppose the space is connected by arcs.
We should take the infim of all the paths, length of the paths, and
this is very good. Yes, and you? Its length is equal to the distance between the points. Yes, yes. This is also very good. It's a path such that its length is equal to the distance between the 2 points. So I have two very good answers. The thing is that, okay, you must define the length of a path in an arbitrary metric space. So this is not, yeah, this is, I mean, it is something. I mean, you have to prove something to have a well-defined notion of length on what sorts of paths. So you will say, well, do I have to take differentiable paths to define the length? And then you say, okay, but in fact, then my space must carry a differentiable structure, or and then you have to say that you have to take approximations of lengths of paths to the minimum. Why does the minimum? I mean, it is very good. It is very feasible. You have to use Ascoli and things like that. There's a very simple definition. So a geodesic in X, well, it's a path that is just an image, just a map gamma, say, from some, yes, just a minute, into my space X, some interval of the real line into my space X. Yes, what did you say? Somebody said something?
Distance between X and Y. Close interval 0, the distance between X and Y.
Yes, distance between X and Y is equal to, yes, but is equal to what? You want the distance between X and Y? So your friend said that I want this distance to be the length of the path, right? This is what he said, and I said this is more complicated. No, the definition is simpler, in fact, such that for any well, 3 points. I take 3 points, x1, x2, x3, in that order in AB. I take 3 points here in that order. Then I have what? Yes, tell me now. Yes, right. I have dx1, x2 plus dx2, x3 equals dx1, x3. So this is a characterization of, I'm using this as a definition, but it's a characterization of geodesics in Euclidean plane, in fact. A Euclidean, so if I take three arbitrary points in the Euclidean plane, I know that the distance here plus the distance here is, well, less or equal to the distance here, right? This is the triangle inequality. But here I'm saying that the triangle inequality is an equality for any 3 points on that path. So, and this is exactly a characterization of the straight lines in the Euclidean plane. A line is a straight line if and only if when I take 3 points, x2, x3, then the three distances satisfy the triangle equality instead of the triangle inequality. This is the simplest definition, and it is the definition of a geodesic in any metric space. Then you will say, okay, but some metric space, like I take just the union of these 3 points. So what is there's no path, there's no continuous path from here to, so in X. So this is for connected by arcs. Yes, it must be metric space connected by arcs, and this is the general definition of. Wait a minute.
Yeah.
Yes, you are right. You are right. You are right. Instead of x, yeah. This is gamma. You are right. Completely right. Thank you. Yeah, this is a mistake. F of gamma of x1.
You can as well put them in gamma x.
And here you have to put gamma x2. Yes. Thank you. I missed this. Gamma x3. Yes. Thank you. Yes. In fact,
Because of the order.
yes, because of the order. Because of the order, this order is very different. This order, if you change order, then here I put x1, x2, and x3 the names of the points on the image. So
Order is in AB.
No, but this will also be gamma x1, gamma
No.
only x1, x2.
yeah, because the picture I drew here, I put x1, x2, x3 as the points, whereas here I have, so I should take T1, T2, T3, and then x1, x2, x3. Yes, I'm sorry. Okay. So now you have, yes.
So not a closed geodesic structure. Sometimes the x1 and x2
Yes.
with other ways.
Yes. In fact, he has a very good. So this is the definition of a geodesic. So yeah. So when you have closed geodesics and so on, then you say that these are locally geodesics. Because yes, you see. So your friend here is saying, okay. So this is an abuse of language. When I say. Suppose I take a closed geodesic here, and I take 2 points. Well, I have on one side, yes, this is distance minimizing. This minimizes the distance between the 2 points. The big one, the big arc does not minimize the distance, but this is so. In general, we say that this is a geodesic, and then the closed curves are local geodesics, but we forget the term local, yes, because we will deal a lot with closed curves, yes. Okay, so this is this is one thing I want to say about pairs of measured foliations, transverse measured foliations. So maybe I want to
Are these foliations due to Teichmüller or did someone?
Yes, no, he introduced the foliations. He introduced the measured foliations, yes. So you see, so there's this, I will talk about this later, and if you remember, there's this Thurston metric. If you remember, it was on first Thurston distance, a distance between hyperbolic surfaces. This is the original. I explained. I will talk about this later, but I will recall. But this, I have a distance between hyperbolic surfaces. So now, and you remember, I was considering best Lipschitz maps between hyperbolic surfaces and minimum of Lipschitz constants of Lipschitz maps and so on. And then I said we have Lipschitz maps between ideal triangles, and then we make Lipschitz map between surfaces and so on. In fact, when you have learned this, and when you know the existence of these singular flat metrics, then naturally comes the problem: what about Thurston metric on the space of singular flat structures? Singular flat structures on a surface. So I have a singular flat structure. Given by two measured foliations. I have a space. I can make it a space, in fact, of singular flat structures, because I can vary the singular flat structures and so on. So, first question: what is the best Lipschitz map between two singular flat structures? This I cannot give you the answer because it's a research problem, in fact. It is very natural, and everyone working on Teichmüller theory who knows about Teichmüller metric and Thurston metric, he says, okay, but now instead of, because the distance between hyperbolic surfaces, so I'm taking about this, about surfaces with hyperbolic metrics, whereas here, you see the Teichmüller metric, this is related, I explained to you, this construction is related to Teichmüller metric, but Teichmüller metric does not worry about the actual metric on the surface induced by these foliations, since we only need to consider the complex structure. Teichmüller metric is concerned with the complex structure on a surface, not with a metric. The metric comes because, okay, there's a natural way, and a fruitful theory of transverse measured foliations, which give a metric, but I'm not going to do anything with the metric, but except with the complex structure. Now you say, okay, but now I want to worry about the metric. And I have all this space of singular flat structures on the surface, and I want to mimic Thurston's theory for this space of singular flat metrics. So how how can I do? I thought about this with my collaborators, and we don't have anything interesting on this. But I think that this is a subject which is a good subject for someone who has time and who can spend time on this. We have some results on. We have some results, you know, on like subsets of the plane, which are. I think I showed you this. I showed you this picture here, which are rectangles of the following form. So Euclidean rectangles, which you glue like this, and they are equipped with singular flat structures. So what is the Thurston distance between this one and this one? And how can you describe the geodesics? So just in simple cases, but not in the general case of a singular flat structure on a surface. This needs work, in fact. Okay, so this is a question. Yeah, before the yes.
You gave a inequality W metric less or equal to K1 of Thurston metric less or equal to K2.
Yes. Yes.
From that relation, can we say anything?
No, because that relation, for that relation, it considers only points of Teichmüller space in the for the Teichmüller metric only as complex manifolds, complex surfaces. I don't need a metric. I don't need a metric on the surfaces. I'm measuring distances of the complex surfaces. Yes, you're right. Thank you. So I want to say another thing before I go to my PDF, to my slides. And this is about okay. You remember we had this notion of measured. Okay, no, let me start in this way. Let me start in another way. So I have a hyperbolic surface. I have closed geodesics. I remind you of this theorem, and this is called theorems due to Hadamard. I don't know, I would say 1920, something like that. Each simple closed curve, non-homotopic to a point, has a unique geodesic representative. In each homotopy class of simple closed curve, I have a unique geodesic. And then we said, in fact, yes, because if I have two curves on the surface which are homotopic, it means that there's a homotopy between them, and they are kind of bounded apart from this homotopy, and then I can lift the homotopy to the hyperbolic plane, and then the lift of the homotopy will give me a homotopy between two geodesics, which is not possible because they cannot be. They cannot be finite at finite distance. The geodesics are like this. Now, what I want to say now is that each measured foliation not only each closed geodesic, has a geodesic representative. So this is on a hyperbolic surface. Let me justify this. This is complicated, but I want to give you the idea of how you prove this. Okay. I come back to a simple closed curve on the surface like this one. This is not a geodesic. And I said that there is a geodesic representative. One way of understanding this, you see, my surface is hyperbolic. So I have the universal cover, which is the hyperbolic disk. And I look at all the lifts of this simple closed curves because this is simply connected. Every leaf will the lift of every leaf will be. So you see, the lift means I take a point here, which maps. I take a point here. I take a point in the universal cover, which is sent to this point. And then this curve, I traverse this curve, and I have one way of continuing here, just because there's a local homeomorphism from here to here, right, which is an isometry for this hyperbolic metric, and then I continue. I arrive to this point here. This is another lift of this point, and then I continue turning. I continue indefinitely in both directions. Now it is a theorem, not. You have to prove when you do this. You have to prove from time to time. You have to prove that when I do this thing, when I lift this curve, I converge to two definite points. From when I lift this curve, doing it from one side and from the other side, I converge to two definite points on the boundary of the space. This is not trivial. This has to be proven. And I do this. This point has many lifts. So this is also another lift. This point, it has lifts here, but also it has lifts. You see, the universal covering is mixing many curves here. This is highly non-compact to this compact surface. So I have many lifts which must go here. This is infinite area. This is finite area. So, okay. So anyway, I lift. And then the thing which is non-trivial is to say that every lift, because in principle I could have a lift. Okay, I continue lifting, and then the lift will accumulate. Why not? Will accumulate, but this does not happen. This is hyperbolic geometry. Tells you, a few lemmas of hyperbolic geometry, which tell you that when I lift this curve, all the lifts converge to two definite points in the universal cover, and then I say, okay, now I'm happy because I know what will be the geodesic in the homotopy class of this curve. I replace each of these lifts by the geodesic that has the same endpoint, and I project again on the surface. And this projection will give me exactly the geodesic which is in the homotopy class of this curve. This is how you prove that, how you construct a constructive proof of the fact that each homotopy class of non-trivial curve is represented by a unique geodesic. It's not easy. I mean, if you don't understand, don't worry. I mean, if you want to understand this, you have to work a little bit. I can give references. Now, the thing which is a little bit more difficult, and which is, I mean, needed in this theory. Instead of a closed curve, I take a measured foliation on the surface. I take a measured foliation. A collection. You see, we always represented the measured foliation locally here, but one good question is, I will continue this sentence there, but one good question here, suppose I have a measured foliation, so I take one curve here, one leaf of the foliation, and then I continue indefinitely on the surface. The surface is compact, right? And then a good question is, what can I say about the limit, or what can I say about the closure of this leaf? So here I can continue. The closure of this leaf, it's a closed subset of the surface, but what kind of closed subset? And here you have, I mean, you have it's not, I mean, it's not difficult, but it's a natural question. And so for instance, do I have leaves which are dense in the surface? The closure of the leaf, can it be the whole surface? You think about the torus case. We discussed the torus case. When the slope is irrational, then the leaf is dense. When the slope is rational, then it's a closed leaf. And it turns out that in the case of arbitrary measured foliations, the closure of a leaf is either a curve, a closed curve, or it is a subsurface. Yes, a subsurface, and in this subsurface, the leaf is dense. It's a subsurface. It's not necessarily the whole surface, you see, because I could have, well, here a measured foliation on this surface, and here a measured foliation on this surface, and then I glue them, and the leaves here will never go to the other part. So there is this question of subsurface here. Anyway, so now you do now you do the same thing which I did here. Instead of doing for closed curves, you will do for the curves which are leaves of a measured foliation. Each leaf of a measured foliation, you will follow the you will argue here in the upper half plane on its lifts, and you will show that each lift has two definite limit points on the boundary of my hyperbolic disk, and then you say, okay, I want to replace each leaf by the geodesic connecting the two limit points. I get a collection of geodesics, and since everything is compatible, you know, I'm doing this. So this is the universal cover of this. I'm doing on all the lifts. On all the lifts, I'm doing the same thing. So the quotient is something, a geodesic representative of my measured foliation. And this is called a geodesic. I didn't talk about the measure, but since I have here a measure, the result also is a transverse measured lamination, a geodesic lamination. Yes? What? Ah, okay. It's time for tea. Okay. I think I will not be able to do whatever I wanted to tell you. I'm a little bit sad for this, but I will tell you as much as I can for now with the slides. It will be more, it will be quicker, in fact, more effective.